Hi everyone, today we're going to be going over the Neoproterozoic oxidation event. So I have a video about the Great Oxidation Event, or the GOE, and this video is going to be very similar to that one, but instead about the Great Oxidation Event, which occurred over 2 billion years ago, we're going to be talking about a more recent oxidation event, which occurred in the Neoproterozoic, or the late Proterozoic eon, which was less than 1 billion years ago. So much more recent, and also distinct from the Great Oxidation Event, and that a lot of the things that caused this event were very different than what caused the Great Oxidation Event. So let's get started. So here's kind of the outline of what we'll go over today. We'll go over what the NOE is, when it occurred, how we know what our evidence is, what caused it, as well as how it changed the environment and biological evolution. So the first two questions are what it is and when did it occur. So basically, like I just said, it's similar to the Great Oxidation Event in that it marks an event or period in Earth's history where the concentration of oxygen on Earth was rising. And I say here that Earth's oxygen concentration increased in 2 stages throughout Earth's history, but as you'll see in the next video when we go over early Paleozoic oxygen history, it has been a lot more stages and fluctuations than that, but these are the 2 main stages that are most well documented for oxygen increase on Earth. And these stages were, like I already said, the GOE, which occurred around 2.4 to 2.1 billion years ago and was caused by cyanobacteria, which we talked about in that video if you want to check out the GOE video, which I will link right here for you. And the NOE, which is the Neoproterozoic oxidation event, shown here on this graph at the bottom here, occurring around 800 to 542 million years ago. And this first stage during the GOE is thought to have risen Earth's oxygen content in the atmosphere to about 10% of today's levels, whereas the ocean during this time remained largely anoxic, so without oxygen, whereas the NOE is thought to have increased oxygen enough to support complex multicellular animal life, which evolved around this time. As we know, around 600 million years ago, we had the Ediacaran fauna, then we had 542 million years ago, we had the Cambrian explosion, and all of that stuff. So this oxygen rise is thought to have a lot to do with that, and some even think during the NOE that the ocean became fully oxygenated, similar to today's modern levels. But this remains largely controversial, and if you're curious and you actually want to go into researching this, there's still a lot that we don't know. For example, the cause, the timing, and the extent of the NOE is not very well constrained, and we do have evidence, but it's just whether we're interpreting it right. So I'm going to run through a lot of our evidence for this event, as well as what we think caused it and ended it, etc. But in the next video, we're going to talk about the early Paleozoic oxygen history and how there are alternative theories to when oxygen actually rose to today's levels in the atmosphere and ocean, respectively. But before we get into our evidence as well as what caused this event, we need to talk a little bit about what was going on during this Neoproterozoic time to get oriented with this time period in general. So during the Neoproterozoic, around 800 to 542 million years ago, there were major climatic swings occurring. Like we already discussed, the NOE is the result of these major climatic swings, and we'll talk about that later more. But there was also tectonic events like Rodinia breakup. Rodinia was a large supercontinent that began breaking up around 800 to 750 million years ago and reassembled after that into another supercontinent like Gondwana, and all of that was occurring around this time. And then also in terms of biology, we had major innovations going on at this time, like the evolution of the Ediacaran fauna and the Cambrian explosion, where before that we really didn't have any large complex multicellular life. So this was a time of really huge events and important ones. So now we're going to get into the evidence that we have for the NOE. As we can see on this slide, we have carbon isotope evidence, sulfur isotope evidence, sulfur carbon ratios, strontium isotopes, redox sensitive trace metals, rare earth elements, and fossils. And what you can notice right away is that a lot of this evidence is geochemical and a tiny bit of it is physical. And so you might be tempted just to leave this video right now because you don't want to hear about all this chemical isotope stuff, but I promise you we're going to walk through it step by step, and it's going to be so cool because these isotope excursions or spikes and stuff match up with all of our physical evidence. And what I mean by this is the time scale, the geologic time scale, was built on fossil evidence, physical evidence. And as you'll you'll see as we get into this evidence, you'll see all of these isotope spikes and all these geochemical spikes in our data that line up exactly with our boundary times. For example, when the Ediacaran started, when it ended, when the Cambrian started, all of those times line up really well with this chemical evidence. So before I go on too much on this, let's move to the first line of evidence, which is our carbon isotopes. If you are uncertain on how carbon isotopes fractionate and what their patterns mean in terms of high carbon isotope values versus low and all of that, you can watch my carbon isotope video. But basically what this graph is showing is some spikes of carbon isotopes throughout time, going from oldest to youngest, right to left. On this graph, we have the GEO, the Great Oxidation Event, as a yellow bar here, and the NOE, the Neoproterozoic Oxidation Event, as our green bar here. And we can see in both cases, the carbon isotopes are spiking dramatically. And so what does this mean? Well, these high spikes of carbon isotopes is just indicative of increased carbon burial. And if you've seen any of the other videos, you know that increased carbon burial means an oxygen source. Oxygen builds up in the atmosphere due to carbon burial because it's not being used up to oxidize that organic carbon. And so in the case of the GEO and the NOE, we see these positive spikes in carbon isotopes during those times. But after the NOE, we can also see a huge negative spike. And this negative spike, opposite to the positive spike, indicates a period at around 580 million years ago of oxidation of a large pool of dissolved organic carbon, at the peak of which coincides with the diversification of Ediacaran fauna. So this is a huge indication that those animals that were evolving, the Ediacaran fauna, used aerobic respiration to oxidize that organic carbon material. But let's take a closer look at this negative spike of carbon isotopes. So now we're looking at this negative spike in carbon isotopes along a graph that goes from oldest to youngest, from bottom to top. And this negative spike in carbon isotopes, which is called the Sturm excursion, looks broader on this graph just because we've expanded that scale. Now, this excursion of carbon isotopes is fundamentally different than any other known carbon isotope excursion. This Sturm excursion reaches well below the mantle value of carbon isotopes of around -6 per mil. And these values below that number cannot be readily explained by organic carbon oxidation or burial. And so originally it was thought that maybe it was due to diagenetic alteration, meaning that these carbonates that were being measured for the Sturm excursion were altered in some way, and the chemical values we were getting were not original accurate values. But so far, too much has gone into this that we are pretty sure that these are accurate original carbon isotope values, as well as they are found in global carbonate rocks during this time. And so we found them in too many places and in too many unaltered specimens that they're really just robust data. And so what does that mean? What else could it be? Well, there's a few thoughts, such as increased seawater sulfate during this time via oxidative weathering, or a shift in the tilt of the Earth could have affected these carbon isotopes, or reversal of oceanic circulation patterns, or global oceanic overturning, but we just don't know yet. And there's a lot of ideas and there's a lot of merit to all of these ideas, and it could have been a mixture of a lot of these ideas, but because this excursion is so complex in its own, I'm going to actually have a whole different video on this Sturm excursion at some point in time. And if I have it out by now, I will put it right here for you guys. But anyway, this is the Sturm excursion, and why it looks so drastically different than all of the rest of carbon isotope data is because we don't know. So anyway, before we move to sulfur isotopes, I'll wrap up the carbon isotope evidence by just saying we know that the positive spikes in carbon isotope values during the GEO and NOE are indicative of rising oxygen levels. And we don't know yet what this huge negative spike means exactly, but more on that to come soon. So moving to sulfur isotopes, we have this graph at the top left showing sulfate versus sulfide sulfur isotope values in the black dots and the gray dots respectively. And then we also have the GEO and NOE plotted on this graph as well. And if you are not familiar with how sulfur isotopes fractionate, and what their patterns mean, then feel free to check out my sulfur isotope video, which I will put right here for you. But the gist of this graph is showing that an increase in the sulfur fractionation between sulfide and sulfate, so basically the difference between the gray dots and the black dots is becoming greater with increased time throughout the geologic timescale. That is reflecting an increased importance of the oxidative part of the sulfur cycle. So sulfate reduction to sulfide is one half of that cycle of sulfur isotopes. The other half is sulfide oxidation to sulfate. And both processes are associated with isotope fractionation, but the oxidative half couldn't really take off until oxygenation of Earth's oceans really occurred. So this data is just reflecting an increased oxygenation of Earth's atmosphere and oceans, increasing the fractionation between sulfide and sulfate. Additionally, we have sulfur to carbon ratios, which is one of the really cool ones. Like I was mentioning earlier, these things happen right at boundaries in the geologic timescale, and this is one of them. And so this sulfur to carbon ratio, as we can see on the bottom left graph, we have this spike of maximum sulfur to carbon ratios during the Precambrian to Cambrian transition right at that boundary, further indicating higher sulfate concentrations in the ocean and a transition from a dominantly pyrite burial regime to sulfate burial regime after the Neoproterozoic and during the Phanerozoic. And we mentioned this briefly earlier when I was talking about that Sherm excursion and how increased sulfate could have played a role in that negative excursion of carbon isotopes. And this here is also corroborating that, in that the timing of an increased concentration of sulfate in the oceans would have lined up with that Sherm excursion, just like this sulfur to carbon ratio does. And so I just mentioned this to indicate the coupling between the sulfur and carbon cycles. But in general, this spike just indicates that there's a transition from reducing conditions to oxidizing conditions in the ocean. Additionally, we have strontium isotope evidence, and if you are unsure about the fractionation processes and patterns of strontium isotopes, then I will link a video right here for you in which I go over elemental and isotopic proxies using strontium. But basically, the strontium 86 to 87 ratio is often used to understand continental versus oceanic input into the sediments that you're analyzing. And so we notice a trend in strontium 87 to 86 ratios from the Cryogenian, which was the period just before the Ediacaran, around 800 to 635 million years ago, to the Cambrian, around 540 million years ago, where we have increasing strontium isotopic ratios. And this increase toward the Neoproterozoic Cambrian transition indicates enhanced continental weathering, which could have fueled higher organic carbon production and burial, and an increased oxygen source to the atmosphere during the latest Neoproterozoic. So if we look at this graph to the bottom right, we see this general increasing trend of strontium 87 to 86 ratios toward the Neoproterozoic to Cambrian transition. And then if we look over here to the bottom left, we have a figure showing how weathering contributes to carbon burial and therefore oxidation of the atmosphere, because silicate weathering by acid rain transports carbon to the ocean where it gets deposited as calcium carbonate, and then to release it back into the atmosphere, it gets subducted, melted, and explodes out of volcano as carbon dioxide. So this weathering part of the cycle acts as the carbon sink, and the volcanic release of carbon dioxide is the carbon source. And so enhanced continental weathering would have caused a lot of carbon burial, increasing oxidation of Earth's atmosphere at the time. And we'll talk about what could have led to increased continental weathering in the section of the video where we talk about what caused the NOE. But now we need to move on to our redox sensitive trace metal evidence for the NOE. Redox sensitive trace metals are one of the most important pieces of evidence for redox events or oxygenation events in Earth's history, because they are sensitive to changing redox conditions, meaning reduction versus oxidation conditions. Some of these elements include molybdenum, vanadium, and uranium. There are a lot more, of course, but these are just to list a few. And shown on this slide is molybdenum and vanadium concentrations in anoxic black shales through Earth's history. So we can see that in these marine sediments, molybdenum and vanadium increase in concentration drastically around 0.5 billion years ago or 500 million years ago. And we can see that this increase aligns pretty darn well with the NOE. NOE. However, we also have the GOE, so why didn't they rise during that oxidation event if oxygenation really is the cause of this spike? Well, that's right, they really didn't rise as much in the GOE as they did due to the NOE, but this is just because there was still so little oxygen in the atmosphere that not a lot of molybdenum and vanadium had been even transported to the oceans yet, because continental oxidative weathering is needed to even transport these redox sensitive trace metals to the ocean to then become incorporated into sediments. So yes, they did increase a tiny bit due to the GOE, but during the NOE, Earth was at a point where it had enough oxygen built up in the atmosphere by now that they could oxidatively weather enough molybdenum and vanadium to transport molybdate and vanadate to the oceans in order to become incorporated into sediment to begin with. And so this trend is really indicative of the NOE. However, there are other lines of redox indicative evidence, such as iron speciation, molybdenum isotopes, and rare earth element patterns that are also indicative of deep ocean oxygenation during oxidation events throughout Earth's history. However, we're going to go over examples of these types of redox indicative evidence in the next video over the early Paleozoic oxygen history, because I just want to spread out these different lines of evidence throughout these different oxidation events throughout Earth's history so that these videos don't get too repetitive for y'all. The last piece of evidence we'll talk about for the NOE in this video is fossil evidence. We talked about how there is a lot of geochemical evidence, but there's also fossil evidence. And you might not think that this picture on the left here looks like a fossil, but it is. And these are fossils of Bavlinella favulatae. Sure, we're going with that. Bavlinella favulatae, which is a species of planktonic cyanobacteria and is characterized by blooms under eutrophic conditions, so over-nutrified conditions. And this genus occurs throughout Ediacaran sections in low diversity assemblages and in large concentrations. And this is evidence for a eutrophic Neoproterozoic ocean, so an over-nutrified algal bloom-rich ocean that would have contributed to atmospheric oxygen increase, because if you know anything about cyanobacteria, like we talked about in the GOE, they're photosynthetic bacteria, and these guys would have populated the surface ocean, photosynthesizing, converting CO2 to oxygen, increasing the oxygen in the atmosphere and depleting it in the deeper ocean. But we'll talk more about ocean oxygenation in the next video. For the NOE, let's move on to what caused this event. We have 4 major lines of evidence we'll talk about. These include enhanced continental weathering, which we already talked about once, volcanic release of oxidized magma, land surface greening and soil production, and ecosystem engineering species, such as sponges. So, the first line of evidence is weathering. We talked about how continental weathering increased, and we know this because of strontium isotope ratios, and this was likely due to something we mentioned earlier, which was Rodinia breakup. Rodinia was a supercontinent which formed around 1 billion years ago and started breaking up around 750 million years ago, right around the time of this oxidation. And this breakup of continents, in addition to the reassembly into Gondwana later down the road, contributed to the increased silicate weathering during this time and the oxygenation. But that was likely not the only way that the Rodinia supercontinent contributed to causing the NOE. The long lifetime of Rodinia led to an insulation effect that increased the temperature of the mantle beneath the supercontinent. And in addition, Rodinia was also surrounded by subduction zones, where a plate of oceanic crust subducts under the continental crust. And these subduction zones enhanced the heating effect of the mantle underneath the supercontinent, because the subducting plates prevent lateral thermal mixing of the mantle. And because of this temperature increase of the mantle, this caused the enhancement of large-scale convection currents in the mantle, because the viscosity was reduced but prevented small-scale convection, and this further prevented efficient mixing of the mantle. And the result of this was hot, poorly mixed mantle beneath the supercontinent and an increase of the melting of oxidized rocks in the subducting slabs, resulting in a large zone of oxidized magma, such as shown here in this green band around Rodinia, showing the subduction zones. We can see it at an even better angle here, where we've cut the Earth in half and we have Rodinia supercontinent here in brown and all of these subduction zones surrounding the continent, and this is causing the emission of oxidized volcanic gases into the ocean atmosphere system, causing an oxygen source rather than an oxygen sink, which is what normally results from volcanic emissions. So this likely compounded the oxidation effect that was occurring during this time because there was no oxygen sink to regulate oxygen in the atmosphere, so it just kept building up. The next line of evidence we'll talk about is the greening of Earth's surface during the Neoproterozoic. This greening refers to the evolution of land plants, which helped to establish an oxygen-rich atmosphere during this time. We can see here to the left that we have a figure showing the distribution of oxygen in pre-850 million year ago weathering environments compared to that of post-greening Neoproterozoic weathering environment, where we have soil production due to land plants evolving and an increase in atmospheric oxygen content toward the top of this soil due to photosynthetic processes. But the soil not only increases O2 levels by photosynthesis, but also by soil production alone. The soil production, which couldn't occur until land plants did evolve, enhanced the continental weathering effect that we already saw was contributing to oxygen increase in the atmosphere due to the breakup of Rodinia. The last cause that we'll talk about for the NOE in this video includes animals. Some important developments that occurred during the Ediacaran-Cambrian transition include expansion of siliceous sponges, decrease in dissolved organic carbon pool in the ocean and therefore enhanced carbon burial, and increased phosphorus removal and seawater oxygenation. So there are a group of scientists that think that this was all thanks to sponges, or at least in large part thanks to sponges. And this is because sponges initiated seawater oxygenation by redistributing organic carbon oxidation through filtering suspended organic matter from seawater. This resulted in an increase in dissolved oxygen, triggering the evolution and diversification of other metazoans. So now that we've discussed the major lines of evidence and the major causes of the NOE, we should probably ask ourselves, what did the NOE cause? For example, how did it affect biological evolution, if it did at all? Well, we can see on this graph we have biodiversity plotted, and we can see this almost non-existent biodiversification rate here, and then we get this huge jump right here and again here. So what's going on there? Well, if we put our bars of the GEO and NOE right here, then we get a much clearer picture of what's causing this biodiversification event here. And so now that we have these bars in place, we probably know that this trend was likely due to the NOE. Now you may be wondering why the diversification didn't increase at all after the GEO. Why did it take the NOE? Well, we can see that the biovolume, so the abundance of biology, did increase after the GEO. It had a big jump right here and increased further after the NOE, but the diversity did not increase much after the GEO. And this is for reasons that I go over in the Life Origins video if you want to check that out right here. But in this video, let's move on to the recap of what the NOE caused in terms of biology and evolution. So we know that this oxygenation event led to large complex animal life, and we just saw that also led to huge biodiversification. However, like a yo-yo, this evolutionary event led to an immediate decrease in oxygen directly after the NOE, and this caused the Ordovician mass extinctions. And so we can see that as we move into the Paleozoic with all of these oxygen fluctuations going on. And so we're going to talk a little bit more about what caused these fluctuations, what resulted from these fluctuations, and all of our evidence for these fluctuations in the next video over the Paleozoic oxygen history. So to recap the Neoproterozoic oxygenation event, we had oxygen significantly rise in the atmosphere and in the ocean a little bit, but maybe not to the full extent that we originally had thought, and we'll get to that controversy in the next video as well. And then we had the evidence for our NOE lying in the redox sensitive trace metals, carbon and sulfur content in black shales, as well as isotopic composition, suggesting that the atmosphere became oxygenated in the late Neoproterozoic, but the ocean may have been delayed in its oxygenation or was subject to more drastic fluctuations before it became steadily oxygenated. And like I said on the last slide, we will be going over those speculations in the next video. But in this video, we also went over the causes causes of the NOE, which included enhanced nutrient supply and carbon burial forced by increased continental weathering, which was likely due to the greening of the land surface as well as Rodinia breakup. And then we also talked a little bit about ecosystem engineering species such as sponges. Lastly, we talked a little bit about the biological ramifications of the NOE, which included increased biodiversification and the evolution of a large complex oxygen-breathing animal life, which subsequently led to more dynamic oxygen fluctuations in the atmosphere and oceans. And again, this is all leading up to the next video over the Paleozoic oxygen history. So for now, thank you so much for watching. I hope you go and check out the Paleozoic oxygen history video because I've said it like 50 times now. So I'm sorry for annoying you, but these two really do go together and I just couldn't fit all the information into one video with a reasonable time period, and I didn't want to make y'all watch an hour-long video, so please go check that out. And with that, thanks again for watching, and I can't wait to see you guys next time. Bye. Fabulina, Fabulate. I want a latte. I want to say that. And carbon and sulfur. Jeez Louise.